All right, so taking a look at another integration technique. This one's called partial fractions. And you're going to take a fraction and break it up into some different pieces, hence the term partial. So here are your essential questions. Go back once you've actually done some work and answer those. But what we're going to take a look at is what our goal is with the technique and how it's going to work. So partial fractions, the goal is that we're going to break apart a denominator that we have, and actually it's going to be a common denominator that we find. So you're going to end up taking a fraction that has a common denominator and then splitting it into a bunch of smaller fraction components, the partial term. Okay, so your first step is to factor, and you do have to remember that when you are factoring the denominator, you have to use powers if things repeat. Then for every different factor, you pick a different letter of the alphabet. I mean, it really doesn't matter, but usually we'll start with A, so A, B, C, and go on. For quadratic factors, then you have to bump it up a little bit, and that factor would now be an AX plus B or a CX plus D. So I'll show you what I'm talking about here. So for example, if we had some repeated factors, so I make up like 2x plus 1 to the fifth, then these steps that they're showing me here would turn into, okay, this first portion would be the 2x plus 1, and then this would be 2x plus 1 squared, and I would work my way up until I had 2x plus 1 to the fifth. Notice in between all of them, I separate them with plus signs. And then all these different, they use, like in the book, a sub 1, a sub 2, and so on. But really what we tend to use when we're working it is a and b and so on. Okay, so if I had 5, I'd a, b, c, d, e. Okay. You can, like I said, though, make up any letters you want. So if you wanted to do A1, A2, like and deal with the subscripts, that would be fine as well. Then you're going to end up setting the numerators of your original and your new fractions that you get a common denominator for. You're going to set them equal. So we're going to set the numerators equal to each other. And then you're going to have to solve for your A, B, C, and so on that you made up. There are lots of different ways to do this. This will be the algebra part of what we do. There are several techniques, or there are a couple main techniques I'll go over with you. And then, oh, sorry, I didn't mean to close that. Just a reminder that a lot of times you end up seeing natural logs for this because we end up switching our problem into the 1 over u or du over u format, and so you end up getting natural logs a lot of the time. I do want to add one thing to this, building off of the idea that we had up here so that your notes have what I want them to in it. So down here, just make a note that if you were to have something, I don't care what's on top, so just leave it blank, x squared times x minus 5, and that's your denominator. So the x squared part is the repeated factor. You'd have to have a portion over x. You'd then have to have a portion over x squared, but the x minus 5 is not repeated, so then you'd have to just have that one time. Okay, so whatever was up here, you would just leave it, and then this would have an A and a B and a C. Okay. All right. Now we'll break up the examples that we're doing. I think we're going to work out 3 all the way. And I gave you 2 pages for each time that we're doing that because there's just quite a bit involved with the algebra portion and then going back and doing the calculus portion. I'm going to separate this video into 2 portions as well. So at first we're just going to talk about how you get the partial fractions set up. Then I'm going to leave it for a little bit. We'll leave some space, and I'll tell you just what you would end up getting for A, B, and C, and we'll go ahead and finish out the calculus. And then I will have a separate video that talks to you about the algebra techniques as far as finding A, B, and C. So in this unit where you're trying to integrate a lot of different things, you always want to start by seeing if like regular U sub would help you. And so that would be a good place to start, is looking at if U is x cubed plus 2x squared plus x, then du is your 3x squared plus 4x plus 1, all that in parentheses, times dx. Sometimes you will find a connection between this and your numerator, but in this case I don't. And so that's a situation where you could know, okay, regular U sub isn't helping me, and I actually don't have to complete the square here because I see some common factors. So this is an alternative to completing the square. Completing the square was helping you force something to factor. This is if it already does factor. So that would be a strategy, is to go off to the side, say, hey, I can take an x out of that denominator and then get x squared plus 2x plus 1. Then I can look in the inside for that quadratic and factor it more, use x, and then plus 1 and plus 1, so x times x plus 1 quantity squared. Okay, because we want to use powers when that's repeating. So then I have turned this problem into the integral. The top is staying the same, 5x squared plus 20x plus 6. The denominator is now factored, x times x plus 1 squared dx. And so now I'm going to split that into partial or little baby fractions. I'm going to have capital A over x, then I'm going to have capital B over x plus 1 plus capital C over x plus 1 quantity squared. And all of that is in parentheses times dx. Okay. The repeated factor, that's why we're using the powers, you have one fraction with it to the first power, then another fraction with it to the second power. Okay, then it's time for us to get a common denominator. Oh, hang on, I wanted that to switch colors. There we go. It's time for us to get a common denominator. So this is just algebra review. How do I take those three fractions and algebraically manipulate the tops to get a common denominator? And you might say, well, that's a waste of time because it started that way. Well, yes, it did, but I want to figure out, what do I do with this A, what do I do with this B, and what do I do with this C? So the common denominator is the x times x plus 1 quantity squared. The first part is missing the x plus 1 quantity squared, and I changed the top and bottom. The second part is missing one of the x plus 1s to make it a quantity squared, and it's also missing the x part. Probably should have put that x part first. It's a little nicer, but that's okay. And then the C fraction, the last fraction, is just missing the x to get a common denominator. Well, then the last page was telling us you need to now set your numerators equal once you've gotten the common denominator. So we get a common denominator, then we set the numerators equal. So that means now I'm working with 5x squared plus 20x plus 6. I need to make sure that that numerator equals A times x plus 1 quantity squared plus, now I'm going to do B and then the x, the little part first, times x plus 1 plus C times x. Okay. We need to solve for A, B, and C. I need to know what to use for A, what to use for B, and what to use for C to make these equal. And that's where I was saying, okay, that's the algebra portion, and I can help you with that. Right now, the calculus idea is you take the denominator, you factor it, You then use little bitty baby fractions along the way to build that denominator up. You get a common denominator, you set now the numerators equal, and we're going to force this to work out. Okay? So you have, like I said, 2 pages. I'm now going to skip and just tell you what A, B, and C are and finish out the calculus part. So I'm going to do that on the next page, just so I make sure I have enough room to come back and do the algebra. So it turns out that A is equal to 6, B ends up equaling, let me find it, -1, and C ends up equaling 9. So I am now integrating, it was A over X, so I'm integrating 6 over X, and then plus we had B, so -1 over X plus 1, and then plus C, oh, sorry, I know what C is, so 9. Switch over, there we go, over X plus 1 quantity squared. Then all that in parentheses dx. And now to finish out the calculus, you can see the natural log rule showing up a fair amount of the time in the first couple of ones. So this would be, hopefully you get to a point you don't need to write it every time, but if you need to see u sub, if u is x plus 1, du is dx, so that works out okay. Here you can do the same u sub, so that would turn this one into -1 over u, and that would turn this one into 9 over u squared. That would mean -1 over u is the natural log rule. This one you're going to think about 9u to the -2. All those would involve du. But like I said, hopefully you get to the point you don't have to show that every time. So this is going to turn into 6 natural log absolute value of x. This is going to turn into negative natural log absolute value of u, but u was x plus 1, plus 9u, which is x plus 1, to the -1 over -1, plus c. Again, if you need to take the time, this is negative natural log absolute value of u. This is plus 9u to the -1 over -1, and then plus your c. But notice I can have all this as my scratch work, however much of it I need, and then I can actually just say these red parts are what's equal, and I don't have to keep recopying the 6 over x over and over and over again. Okay, so final answer, you're going to see them probably flip that last part with the 9 around. So 6 natural log of absolute value of x minus natural log absolute value x plus 1 minus 9 over x plus 1 plus c. Some good times to try integration by parts. When we see that we can factor the denominator and regular u sub isn't helping us. Also, if we're working multiple choice and we see answers that have a ton of natural logs in them, you end up with a lot of natural logs because of how these fractions work out for partial fractions. So that can be a clue as well that, hey, partial fractions might help me. So that was the calculus. I will come back, like I said in the other video, and show you how to get A, B, and C. But looking at the next example, trying to get the calculus part down. All right, you try regular u sub, but if you notice, they've already factored this denominator for us. Not all the way, I can go one step further, but that's where it's a good idea to try partial fractions. So if I take a look and recopy my numerator, 2x cubed minus 4x minus 8, and then the denominator, I can take out an extra x from there. So x times x minus 1 times x squared plus 4. And since it's a plus, I can't factor that anymore. Dx. and then that needs to equal, I'm going to do all the little baby fractions. I'm going to have a over x, my first denominator piece, plus b over x minus 1. Oops. And then plus c, well, not quite though, because this is a, oh my goodness, sorry, I keep hitting the one to exit out. C, it's not going to be just C because this is a quadratic, change colors, this is a quadratic factor. So since it's a quadratic factor, I'm going to do Cx plus D for my numerator. And then over x squared plus 4. And I'm doing that because of this squared. If you go back to our last example, you may say, hey, why didn't we do it here because this was squared? The actual factor itself was linear. X plus 1 was linear. It was just repeated with a power. In my example here, the factor is x squared plus 4. It's not that it's repeated over and over. It's the factor itself is quadratic. So if that's the case, your numerator would be ax plus b or cx plus d or whatever you need to make it work as far as the a's and b's, but it needs to have an x in it. Okay, then we want to get common denominators. So we go up and say, okay, this is my common denominator. What's missing from the a over x? Well, it's missing the x minus 1 and the x squared plus 4. And I have to change the top and bottom because I have to keep it balanced. What's missing from the b term? So the x minus 1 also needs an x, and it needs an x squared plus 4. And this gets kind of crowded. And then what's missing from the last one? Well, it's missing the x, and it's missing the x minus 1. So cx plus d goes in parentheses, times x minus 1. Okay, then we need to set our numerators equal to each other. Okay, so we're going to take 2x cubed minus 4x minus 8, and we're going to set that equal to a times x minus 1 times x squared plus 4 plus bx times x squared plus 4 plus cx plus d in parentheses times x minus 1. So this one is definitely more complicated. Okay, but we are now at the point where this would be the algebra idea of how do I find, so I need to solve for A and B and C and D. And I will go back in the other video and talk to you about the algebra involved for that. Okay. Next page, we'll finish up the calculus for this. So it turns out that A is equal to 2, B is equal, why is it not working? C is equal to 2, and D is equal to 4. So I have now rewritten my integral. It was a over x, so 2 over x, plus b, so negative 2, over x minus 1, plus cx plus d, so 2x plus 4 over x squared plus 4. All of that times dx. And now the calculus portion is how do I integrate all of these and finish them out? So as much work as you need to show in order to do that, there really is a u sub idea going on here where u is x minus 1, du is dx. You could try a u sub idea going on here where u is x squared plus 4, du is 2x dx. I don't quite have that, so this one gets a little more tricky. What you can do is split this up into, so integral of 2 over x, and then I'm going to bring the minus out in front, minus 2 over x minus 1, and then I'm going to split this last part. And a lot of you might say, well, I can't because there's more than one term in the bottom, but I can take the one term on top, the 2x, and put it over x squared plus 4. I can't break apart the denominator, but I can break apart the numerator. So 2x over x squared plus 4 over x squared plus 4. Okay. And the reason I'm doing that is because this u sub is going to help me here. And then this u sub I can now make work since I split apart my numerator. And now for this one, I'm going to rethink about this as 2 squared. Think about this as x squared. This is an arctan setup. Okay? So if u equals x, du equals dx, that 4 can just be thought of as a constant. And my a term will be 2. Okay. You can show as much or as little scratch work as you need in order to be able to do the calculus portion accurately. Okay, this portion will be turned into 2 over u. This portion will be turned into 1 over, but this is another u, a different u value. You may want to call them u1 and u2 so you can keep them straight, or you can pick different letters for each one, however you want to do that. And then this is a 5.9 tangent inverse setup. Okay. So as I go through, this becomes 2 natural log absolute value x. This becomes negative 2 natural log absolute value. That u was x minus 1. This becomes plus just 1 because of the 1 on top, natural log absolute value. Well, that u was x squared plus 4. And then this part, you had a 4 in front. The inverse tangent formula involves 1 over a, so 4 times a half. Then tangent inverse of u over a, so x over 2, and then plus c. Again, if you need to show some in between, this integrates to be 2 natural log absolute value of u. This integrates to be just natural log absolute value of u. But they have different u's, remember? And so then when you go to replace them, that's why these portions are different. To clean up for your final answer, we're not going to leave 4 times a half, and we also don't need these absolute values on the x squared plus 4, so they're probably going to get rid of them. So 2 natural log of absolute value of x minus 2 natural log absolute value x minus 1 plus natural log parentheses x squared plus 4 plus 2 tangent inverse or arctan x over 2 plus c. Also with multiple choice, they can be clever with exponent rules and natural logs, like switching them over to either natural log of several things that are multiplied or natural log of things that are divided, or a combination of the two, using all those algebra rules that you can do for natural logs. Okay. The scratchwork stuff that I have up here in green, those things are optional as far as you showing them at this point. If you can get the right answers and do the calculus knowing what the u sub just is, you're welcome to show only what I had in red here, and that would be totally fine. Okay, last example that will work out all the way showing all the calculus stuff, and then we will go back and do the algebra stuff. All right, this one's already factored for us. It's a repeated factor. So as I switch it over, so I have 8x cubed plus 13x all over the x squared plus 2 squared dx. That's going to equal, well, it's a repeated factor, so I need it twice. One time I need to have x squared plus 2 as my factor, and the other time I need x squared plus 2 quantity squared. Also, though, it is a quadratic factor. So because I have the actual factor itself involving a quadratic, that part and that part, then that means what I'm placing on top is not just a anymore. It should be ax plus b. Not just c anymore. It should be cx plus d. Okay, then I need a common denominator. All that's missing here is I need to make it squared, which means all that's missing on top is an x squared plus 2 just one time. I need to set my numerators equal. So 8x cubed plus 13x needs to be equal to ax plus b times x squared plus 2 quantities for each one, parentheses for each one, plus the quantity cx plus d. Okay. So stepwise, we got it set up. Then you do common denominators. Then you do numerators equal. And then you need to solve, in this case, for A all the way through D. All right. Again, that'll be in the algebra video as far as how you do that. You do have more space on the next page to finish out the calculus portion. You end up with A is equal to 8, B is equal to 0, C is equal to -3, and D is also equal to 0. Those zeros are kind of nice. So that means really I'm integrating, it was ax plus b, so 8x plus 0 over x squared plus 2 plus, and then it was cx plus d, so -3x plus 0 over x squared plus 2 quantity squared. You're not always going to end up with zeros, but it's kind of nice if we do. Oops, I did that again. Okay. Now for the calculus portion, as you take a look at integrating, these are good setups for regular u sub because the factor in your denominator is quadratic and both of these have x's in the numerator. So let's try regular u sub with x squared plus 2. Du is 2x dx. And I can make the 2, I could just do 1/2 du and think about the x dx. This 8 I can do other things with. It's a constant. I could think about it coming out in front. The -3 is a constant. I could think about it coming out in front. So it depends on how much work you need to show. But really, if you need to show all of your u sub, this would be 8 times 1/2 times the integral of 1 over u du. And then it would be minus 3 times 1/2 times the integral of 1 over u squared du. You would be thinking about this one as 4 integral 1 over u du. You would be thinking about this one as -3/2 integral of u to the -2 du, because you can do regular power rule here with it being a -2. You can't do regular power rule here because if you add to the power you get 0, and if you try to divide by 0 that's a problem. Okay? So then back to integrating, and like I said, all this u sub stuff, you can show as much or as little as you need to at this point. This integral is equal to the, not integral anymore, it's just equal to 4 times natural log absolute value of u, so x squared plus 2, and then minus 3 halves times u to the negative 1, so that would be x squared plus 2 to the negative 1 over negative 1, and then plus c. And then going to clean everything up, the natural log doesn't need absolute values anymore because the squared's already positive and you're adding to it. Going ahead and looking at this, you have a double negative and fixing your negative exponent. So final answer, you would probably see 4 natural log of parentheses x squared plus 2 plus 3 over 2 times the quantity x squared plus 2 plus c. And again, if you need more of the scratchwork step, like if you need to show that this is u to the minus 1 over minus 1 before you replace it, that's okay. If you need to show that this is natural log of absolute value of u, that's okay. But if you're getting to the point where you're still accurate and you can combine more of those steps, go for it. Okay, so that finishes out explaining the calculus for partial fractions and explaining all of the setup and why we do what we do. Then, like I said, in the other video for the algebra, I'll go over how do we find these A, B's, and C's in the best, most efficient way possible. Okay. I also want you guys to try the AP example and see if you're able to come up with it. You can see some things we were talking about, that partial fractions is a good idea because you see these factored. Partial fractions is a good idea because you see all these involve natural logs, and as you've seen in our examples, we end up with natural logs quite a bit. So those are some ways you can pick it out. I want you to see, once you've gone through, if you're actually able to do this example. So I'll record another little short video for just this part, but you actually try it on your own.